This episode of the n-Lorem Patient Empowerment Program podcast is proudly sponsored by Hongene Biotech. With more than 26 years of experience in the nucleic acid industry, Hongene is a specialized CDMO and raw material supplier committed to providing high-quality and high-value products and services with the best-in-class lead times.
Nearly half of all Patient Empowerment Program episodes are centered on our Intro to Medical Science series, a masterclass on the basic science behind drug discovery and development, because rare diseases often cause people to quickly immerse themselves into this world while making significant health decisions. These episodes provide knowledge that empower rare disease families as they navigate this new complex landscape. There are over 30 Intro to Medical Science episodes available right now. If you enjoyed today's discussion, be sure to explore more topics in the series like what is an ASO, how to think about risk, advanced genetics, and many more by clicking the YouTube playlist link in the description.
The following episode of the Patient Empowerment Program was recorded in 2022.
Welcome to the n-Lorem podcast series. Since I founded n-Lorem, I've been involved in many discussions focused on these patients and creating both short and long-term solutions to meet the needs of these patients. And I've been deeply touched and impressed by the number and diversity of the people involved, the energy, the progress, and the commitment of so many people. It involves many academic scientists and physicians, charitable foundations, parents, and patients who are involved. So it really is a very diverse group. I've been particularly impressed with the patients and parents, most of whom have really no basic training in the chemical or biological sciences or medicine, and yet have mastered at least parts of the science and the medicine and achieved really quite remarkable steps. And I think those people are to be especially applauded for their willingness to commit and their ability to learn what, in fact, takes most of us many years of training. I've also been impressed by several notable absences. I've not encountered a single person with any real knowledge or experience in drug discovery and development. And since that's what we are discussing for these patients, that's a critical deficiency. And that is certainly one of the voids that I hope to fill with the series of podcasts that are more lecture-like. So given the diversity of those involved in addressing the needs of ultra-rare patients, I think there may be some real value in briefly going from the absolutely most basic concepts to what drugs are, what they can and cannot do, and how they come to be. I think this will help assure that we all are coming from the same starting line and that we are all using or able to use a shared vocabulary. I'm confident that all of you understand some of this, and some of you probably understand all of it, and some of you may understand it better than I do. But even for those who are fully informed, I think it is sometimes of value to hear the basics from a different perspective, and I hope to give that to you. We will begin with the absolute simplest of ideas. But I promise I will quickly enroll you in a masterclass in what is going to be necessary to broadly enhance the treatment of patients with ultra-rare diseases. Let's begin with this seemingly so simple statement. All drugs are chemicals. And that is true whether you take a prescription medicine, an over-the-counter medicine, or a mixture of natural products or supplements that you get at a natural food store. Drugs differ from other chemicals only because they are administered to humans or other animals for therapeutic purposes. And by therapeutic purpose, we mean that we want to alter the state of the biological systems that result in characteristics that we see in patients, or said another way, we plan to alter the phenotype of the patient. We plan to convert the disease phenotype of the patient to a healthier phenotype, which brings me to the word phenotype. A phenotype is a composite set of characteristics that a biological system, in this case it's a patient, displays at a particular moment. The phenotype of a patient comes to be as a result of the genetic characteristics of the patient, the effects of current environments, and the history of the patient. So the phenotype of a patient today reflects all the experiences the patient has had and all the previous phenotypes expressed. And the next phenotype that will be expressed by that patient will be a consequence of the phenotype that we begin with before we add a drug, and then, of course, the addition of a drug. A genotype is the sum total of genetic information a patient has. You can think of it as the total genetic capability possible for that patient, from which that patient selects those traits that are expressed to create the phenotype that's displayed when the patient comes into our office. A genotype is a product of the genetic information that the patient inherited from his parents, including all the mutations his or her parents had, and any mutations that have happened to the genes of the patient during his life. Almost all drugs, and we'll talk about this extensively, are designed to alter the phenotype of the patient, but not the genotype. On the other hand, when we engage in gene therapy, we're altering the genotype so that a healthier phenotype will be expressed. Many anti-cancer drugs are designed to alter the genotype of cancer cells, and CRISPR and gene therapy are ways to alter the genotype as well. So, first key point, or a key point, drugs are administered to alter the phenotype of patients into healthier phenotypes. Most drugs are designed to alter the phenotype without affecting the genotype. And in fact, we work very, very hard to avoid genomic effects because it can often be very toxic. And of course, they last for a lifetime. Gene therapy and CRISPR are ways to create healthier phenotypes by altering the genotype. Okay, so let's back up to something even simpler, chemicals. So what is a chemical? What do chemicals actually do? And how do biochemicals differ from other chemicals? Our world is made up of molecules that we call chemicals. Each chemical has a unique set of characteristics that establish a unique chemical fingerprint. Chemicals vary in size, and the size of a chemical is measured in units that are called Daltons, abbreviated with a big D because Dalton was a scientist. Size can vary from 1 Dalton to many millions of Daltons. Chemicals can be positively or negatively charged, or they can have no net charge at all. They can be neutral. Of course, we then have all kinds of drugs that have different charges as well. Charge density is the pattern of charge over the surface of a chemical. Chemicals can be water soluble, and scientists refer to that as water liking, or soluble in fat or lipids, and scientists refer to that as fat liking. Some chemicals are called amphipathic. Those chemicals dissolve in both water and lipids. And if you were to have a test tube with water and oil in it, and you shook it up, the amphipathic chemicals would be found at the interface between water and the oil. So all of those characteristics, and many more that I haven't gone into, form a composite set of characteristics for that chemical. And it creates a three-dimensional pattern for that chemical. The three-dimensional pattern for each chemical is different. It's unique to that chemical. Every nanosecond, chemicals engage in a myriad of pattern recognition events with other chemicals. These pattern recognition events begin with a collision between two chemicals or more. The frequency of collisions between two chemicals is a function of the concentrations or the number of molecules per unit volume of each of the chemicals. So when two chemicals collide and they have appropriate three-dimensional patterns, then they can produce a chemical reaction. In a chemical reaction, the two chemicals that began the reaction are changed and they become what's called products. Chemical reaction then is a critical component of life. So this brings us to another key point. Each chemical has a three-dimensional unique pattern. Chemical reactions begin with a collision between two or more chemicals. Thus, all chemical reactions are concentration dependent. Drugs are chemicals. So the effects of drugs must be concentration dependent, and they certainly are. We often adjust the concentration of a drug in a patient or animal by adjusting the dose. And we adjust the dose to adjust the concentration to that which we want to produce a specific effect. Some chemicals are essential for life and create biological systems. And we call those chemicals biochemicals, but they're really just chemicals that we find interesting because they result in who and what we are. Okay, a biological system is a set of networks of chemicals and chemical reactions that result in biological behavior. All animals are, of course, comprised of cells. Of course, you know that. But have you ever asked why evolution bothered creating cells? Well, it's pretty simple. You can think of cells as tiny bags of water in which the chemicals required for life are concentrated sufficiently to support biological activity. So cells are a means to concentrate the chemicals you need in a way that allows them to produce chemical reactions that support life. Our cells are protected from the environment by a very complex, constantly changing barrier that's called the plasma membrane. It's composed of fats or lipids, and some lipids that have a negatively charged phosphate. They're called phospholipids, and then various proteins are integrated in and out of that plasma membrane. So the next key point, cells concentrate the concentration of chemicals so that biochemical reactions can be produced that lead to life. Cells perform several functions. They integrate all the chemicals and the chemical reactions into complex networks that create then the phenotype of that cell, or in the case of a patient, the phenotype of that patient. They constantly sense and respond to the environment by adjusting their phenotypes. They are then integrated with other cells of various types to create organs, and each organ has its own general set of functions. And they come together to create us, to allow us to manage our life. The organs and fluids of the body are integrated then into an even more complex set of networks that are organized in a hierarchical way. And out of all those sets of chemicals and chemical interactions is created a composite set of behaviors. And that's the patient we see. That's the patient's phenotype. And of course, the phenotype of anyone or any cell, animal, person, patient varies, second by second, depending on how he's responding to the environment. Finally, most cells also have to replicate in an orderly way. So they place cells that die of the same type. And so they have to have a process that allows them to make new cells or daughter cells. Brings us to the next key point. You and I are simply incredibly complex networks of biochemicals and biochemical reactions that create the phenotype that we recognize when we look at ourselves in the mirror. Many important biological chemicals are in fact polymers. Polymer, of course, means many units. Poly, many, units, mer. One important type of polymer is proteins. The building blocks of proteins are called amino acids. And for simplicity, you can think of each of those building blocks or amino acids as being about 100 Daltons, pretty small. But when they're strung together as polymers, they become proteins, and they can become very, very large. Typically, we think of a protein as ranging, say, from 10,000 Daltons to hundreds of thousands and sometimes millions of Daltons. And so you can imagine how big those molecules are. They've taken literally thousands and thousands of amino acids and put them together sometimes. You can imagine then how complex the three-dimensional pattern of a protein must be. And that's going to be an important thing to remember as we go forward. Another important set of polymers are nucleic acids. The building blocks of nucleic acids are called nucleotides, and you can think of them as being about 300 Daltons in size, larger than an amino acid, but still pretty small. These building blocks are strung together through negatively charged phosphate groups. And since phosphates are negatively charged, these molecules behave as acids. That is, if you applied an electrical field to a solution of nucleic acids, they'd migrate toward the positive pole. And that's why they're called nucleic acids. Now, there are two nucleic acids that matter. DNA is a giant polymer made up of millions, many millions of nucleotides. And RNA is the other nucleic acid polymer. And most RNAs are typically thousands of nucleotides in size. So now let's go back to cells. Cells are organized like modern corporations. Each cell has a set of employees that do the work of the cell. For our purposes, you can think of the working molecules as proteins. These are the workers. They're in, the shop actually making the products. The polymers then that we think of as proteins are made up of amino acids. Now, there are 20 basic amino acids. So you can think of proteins as using the language of amino acids. And the amino acid language is pretty darn complex. It's almost as complex as English, in which we use 26 letters. The information management system of the cell is quite different. It's comprised of polymers we call nucleic acid, DNA and RNA. And of course, you know that the nucleic acid language is much simpler. It just has 4 letters, A, T, or U, C, and G. And, that set of letters is used in both DNA and in RNA. So this is a vastly, vastly simpler language than the language of amino acids or proteins. You can think of it as almost as simple as the Morse code. And as I mentioned, the DNA in your cell is just almost unbelievably large. It's said that if you stretch the DNA in a single cell, one cell, out fully, it would be several meters long. Now, DNA is used to store genetic information, and the information encoded in your DNA is your genotype. Because the DNA in every cell is so large, the file has to be compressed, and it's compressed into structures called chromatin. And during cell division, they get then sorted out into different things called chromosomes. Humans have 23 chromosomes. That information in the DNA has to be stored and protected at all costs. I mean, this is who you are, and you need to protect yourself. And so you and I and all the rest of us have just a remarkable set of very complex systems that are designed to protect our DNA and to repair damage. Now, damage can happen because we encounter very reactive chemicals that can damage DNA. Many of them are just the products of life, just the biochemical reactions we do. And then others you can encounter in your environment. For example, if you go to the beach and sit in the sun and have UV light, a change in a DNA that isn't corrected by one of those systems is permanent. It's called a mutation. You tend to think of mutations as all bad. That's not true. There are many mutations that can be beneficial to the cell. And if there is a mutation that's beneficial to that cell then will outgrow the other cells that don't have it. You'll end up with a biased batch of cells that we would call a clone. The other way mutations can happen is when the genetic information is copied. And you can think of these mutations as really just typographical mistakes. And you make a copy of DNA when you're getting ready to make a new cell. You also make partial copies of a lot of your different parts of your DNA when you need to express a specific phenotype. So it is an error-prone system. It just is. And so once again, you have a lot of systems in place that follow the typewriter and correct the mistakes that are made. Mistakes that aren't corrected become mutations. So how is the information in DNA used? And of course, you know this, but I'll just walk through this very quickly. When it's time to use the information in a particular gene, that information is converted to RNA. And if it's an RNA designed to make a protein, that's called messenger RNA. And RNA uses basically the same 4-letter code that DNA does. So that process is transcription. That's exactly what it is. You're transcribing a part of the information in your DNA. Now, if the information in the RNA is to be used to make a protein, then the nucleic acid language has to be converted to the much, much more complex language of proteins, the amino acid language. And so that process is called translation. And that's exactly what's happening in your cell. You're taking this information in one language, the Morse code of your genetics, and converting it to the English of your proteins, translation. The reasons these words are used by scientists is that's exactly what they mean. So polymers, key point, are critically important for biological systems. Each cell stores genotype information carefully, and when it needs to use some of that information, an RNA molecule is made. When that RNA is made, that's called transcription. And then if that RNA is to be used to make a protein, the information has to be translated in your cell to make the specific protein. Now, drugs are used to alter biological systems. Let me just say that again. Drugs are used to alter biological systems. Yes, it is conceptually possible today, I suppose, that we could synthesize a new gene and that could then generate new biology. But in most cases, today's drugs are used to alter biological systems. They don't create new biology. They alter the biology that you were practicing before when you take the drug. And so the other way to think of a drug is it alters the composite set of characteristics that are a product of all these gazillion networks in the body to generate a new composite set of characteristics. Or said another way, drugs are used to alter a phenotype that we think of as diseased into a new phenotype that we think of as healthier. So I want to slow here just a minute and make a point that I think is far too often overlooked. Even if a drug were perfectly specific, and there is no such thing, and by that I mean that we're using that drug for one specific desired effect, and it does absolutely nothing else in the body than just that. Even if it's that specific and there has never been a drug that specific, even that perfect drug will alter the composite of all those networks in ways that at the present time are still unpredictable. So there's no free ride with any drug. Even a perfect drug produces a myriad of changes in phenotype that are not today predictable. Equally important is the fact that the networks that create a specific phenotype, let's say a diseased patient, are unique to that patient. And they create a biological environment with which that drug interacts. And so that means that the effects of drugs are often very different in patients with diseases compared to healthy patients. And the severity of disease also can change the effects of the drug remarkably. And so I just can't emphasize enough how tremendously important these concepts are as we think about how to help patients with ultra-rare disease. They can't be ignored. Yes, when you give a specific drug or chemical or agent, you're giving it to do a particular job, but its effects will be defined by all its properties and the nature of the person who takes it. This becomes particularly important in gene therapy because, of course, with gene therapy, we are trying to result in a permanent change in the genome, which could mean a permanent change in all the phenotypes. And so that would be great if you get only what you want. But what happens if you get what you want plus a whole bunch of other things? So in sum then, biological systems generate a phenotype by integrating an incredibly complex array of chemical reactions into progressively more complex networks. These networks determine the phenotype that one presents at a particular moment. Phenotypes change constantly in response to the environment. And when we administer a drug into a biological system, and the effects of the drug can vary as a function of the nature of that biological system. We see very different effects sometimes in patients who are diseased, and we constantly worry about how the effects of a drug may change as the patient progresses in their disease. Important concepts to think about. In the next podcast, we'll now take another step in complexity and begin to think about drugs in much more detail.
n-Lorem is a nonprofit committed to discovering and providing personalized experimental treatments for free for life to patients with genetic diseases that affect 1 to 30 patients worldwide, referred to by n-Lorem as nano-rare. Many of these patients progress and die without ever achieving a diagnosis. This is where n-Lorem comes in. They do the impossible by providing hope, and for those that they can help, free lifetime treatment. For more information about n-Lorem or today's episode, visit n-Lorem.org. Any questions can be sent into podcast@n-Lorem.org. Search n-Lorem on Twitter, Instagram, YouTube, LinkedIn, and Facebook to connect with us. Please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allows others to find the show. This podcast is hosted by Dr. Stan Crook. Our videographer is John Magnuson of Mighty One Productions. Our producers are John Magnuson and Kira Deneen of DNA Today. Thank you for listening.